Okay, so 5.4 is all about properties of logarithmic functions. So we kind of played around with our exponential last week and our logarithmic function in terms of graphically playing around with them, and now we're going to use all these different properties that we're going to learn today on logarithms to play around with our logarithms algebraically. And so you're going to learn a product rule, a quotient rule, a power rule, and a couple of other just of the basic rules. From 5.3, you had a small list of rules, like anything to the 0th power is 1. When the base is the same as what you're taking the log of, that gets you to 1, and things like that. So for our product rule, it says let b, m, and n be positive real numbers, and we can't have b equal to 1. So our base can't equal 1 because then it's pointless. With our product rule, what it says is that if we can have log base b of two different things that are positive real numbers, this m and this n, then we can split those or expand it. Sorry, I put my finger there and then it's going to focus on my finger. I know, it's going to think about it for a second. We can expand our logarithm into two separate logarithms where we have log base b of m plus log base b of n. So the bases stay the same when we separate, and then we put a plus sign in between the two logarithms. Here's the nice thing, is if we can, I don't want to point because then it's going to get all blurry. If we can go from the left-hand side of this equation to the right-hand side, we can also go from the right-hand side to the left. So we can condense our logarithms in this fashion as well, where if we have log of the same base being added together, then we can combine them by multiplying what we're taking the logs of. And we're going to see that as we work through some of our examples. So we can expand by moving from left to right, or we can condense from moving from right to left. In both ways, it's using our product rule. So we're only doing the top two for right now, which is all you can see anyways. We are going to expand or condense depending on what is given to us. We have log base 3 of 8 times 29. We need to expand that using our product rule. Well, I know I'm going to have log base 3 of something plus log base 3 of something based on my product rule. So what is my something? Log base 3 of what? 8. Log base 3 of what? 29. That's it. You're done. It's a whole problem. So don't try to make them overly complicated. They'll get more complicated as we move along, but for the second one, we have log base 2 of p to the 3rd power plus log base 2 of q. Since we have log base 2 for both of those, we can combine what we're taking the logs of by multiplying them together, to where we end up with log base 2 of p to the 3rd q. If those bases are not the same, we can't combine them. If I had log base 2 of p to the 3 plus log base 3 of q, I couldn't combine them any further. So those bases have to be the same for this to work. Questions on how we did that? Okay. Try and scroll up on the back page and leave that front page alone for you. Our next rule is the power rule. The power rule is where we have b and m positive real numbers, b does not equal 1, and we have p is any real number. So if we have log base b of m to the p, so that p is an exponent applied to what you're taking the logarithm of, we can pull that exponent out front to where it says p times log base b of m. So it's not log, but it kind of looks like log. Log base b of m to the p. We can pull the p out front and multiply that by the log base b of m. And again, if we can go from the left-hand side to the right-hand side, which is expanding it, we can condense going from the right-hand side to the left-hand side, where we pull that number out front up as a power. We're going to do 3 of these. Log base a of 11 to the negative 3 power. If we have to expand that or apply our power rule, then we're going to take our power, which is negative 3, and we're going to plop it down front so that we have negative 3 log base a of 11. Sorry, I picked up the paper and messed it all up. That's all you're going to do. Pull that power out front. Now for b, we have log base a of the 4th root of 7. I don't see a power. So where's the power? Yeah, remember we can go from radicals to rational exponents. So 7th to the 4th, like the 4th root of 7th, is the same thing as saying 7 to the 1/4. We talked about this last time, or the time before, I don't remember which one, where the number out front, like on top of your rational exponent, stays with your base, that's in here, and the number on bottom pops out front and becomes the index of your radical. So this is saying log base a of 7 to the 1/4. So sometimes you are going to have to convert between your radicals and your rational exponents. Because now that I have it written like this, I can pull that 1/4 out front. So it's 1/4 log base 7, or base a of 7. And hopefully, even though we're not going the other direction, you can see how if you had this expression, we could take the power rule and bring that back and then work upward as well on these problems. But I believe we had a small section of notes about the rational exponent last time, didn't we? I think there was a small section in 5.3. I feel like it was 5.3. It might have been 5.2, but I think it was 5.3. Okay, what does C become? ln of x to the 6th power becomes what using the power rule? Yep. No tricks there. 6 ln of x. All of these different properties, while I'm giving them to you with log base b, they are still applicable to the natural log as well, because that just means your b in that case was e. So it works for regular logs and rational or natural logs.
It was in 5.2 if it matters.
It is in 5.2. Okay, thanks. So in 5.2, we had a little section on that. All right, so we've done the product rule. We've done the power rule. We've got one more rule, the quotient rule. Now, when we did the product rule, that was when we had two things being multiplied together, and we were able to expand them using addition. So what do you think happens when we divide? Yeah, we're going to do subtraction. Let me see, does this help? No, that does not help. Don't do that. So B, M, M are positive real numbers. B is not 1. Then if you have log base B of M divided by N, we can expand that and separate it using subtraction, where your numerator becomes your first term, and then you put subtract log base your denominator. And just like with all of our other properties, if we are expanding by moving to the right, if we were given something like the right-hand side, we could condense it by moving to the left. Don't do that. Are you ready to try some? See? Then she does it. That's why you can't do it. You can't yawn, because then everybody starts yawning. Okay. We have log base T of 8 divided by W. We are going to expand this using our quotient rule. The top will become your first term. So you'll have log base T of 8. Then you put a minus log base T of W. That's it. What about B when we condense? Okay. Is that simplified? No. 64 is divisible by 16, so we would want to simplify it. Now, obviously, you wouldn't start at log base B of 4 and be able to get back up to this. Like, that's kind of a weird mentality to get to. But if we are condensing, you need to condense as far as you possibly can go. And a lot of times that means you're going to have to do some simplifying if you have fractions and things like that. As we're going to see on the next few examples, there's a couple other little rules that we've had before that are still going to be at play. Like when we have the base that's the same as what we were taking the log of, that gives us 1. We don't want to end up, which we didn't here, but if we would have had log base 4 of 4, we wouldn't just leave it log base 4 of 4. We would go ahead and simplify that down to 1, because that is as far down as you would take it. Are there any questions on how we did our quotients, though, here, or really any of them that we've done so far? Because really, we've only dealt with like one rule at a time, and you know that that's not how math works. We're going to have to do more than one rule at a time. So we are going to expand log base A of x squared y to the 5th all over z to the 4th. Yes?
And so once you do parentheses log A, x2 plus log A by 5, that would
You're close. But I'm going to take it step by step. But you're really close. Okay. So first thing I'm going to note is that I have a fraction, don't I? And if I have a fraction, I can expand this using my quotient rule. Okay? And if I am expanding using my quotient rule, then I have my top term first, which is x squared y to the 5th. That's my top term. Minus log base A of my bottom. But now, if I look at my first term, what's going on there? All right, that's a product rule. So I can expand this further. I can expand it so that I have log base A of x squared plus log base A of y to the 5th minus log base A of z to the 4th. So all of this got expanded into all of this using my product rule.
Whenever you expand it to add the addition sign, do you still need the parentheses?
You don't have to. I always do because it makes it way more noticeable to me what's going to stay on top, but no, you don't. Because what it comes down to is if I don't have this, and I were to do like this part first, and combine this using my quotient, I still will end up having to multiply then this by my quotient, which will still get me back to where I was going. So no, you don't have to. And in the very last step, I usually don't. But now as I look at it, okay, I've gotten rid of all of my division. I've gotten rid of all of my multiplication. So what do I have left? Power rules. So every single one of these has a power that I need to pull out front. So I have 2 log base A of x plus 5 log base A of y minus 4 log base A of z. I cannot spread this out any further. That's as far out as I can expand this. So this would be the end. Questions? Okay. What about this one? How about you guys try and do this one? I'll write out the steps in just a minute, but I want to see how you guys do with it. do. There's a lot of stuff going on this one. A to A. Yeah. Yeah, if the base is the same as what you're taking the log of, then that can go away. And that'll be very helpful as you get into some of these ones like this where it's a little bit longer. So first thing I did was I switched obviously from the radical into the rational exponent. Then I applied my power rule to pull that out front. Then I applied my quotient rule to split that fraction up. Then I had to apply my product rule in here to split that all up. Then I applied my power rule again inside my parentheses. Then I got rid of my log base A of A because that's 1. And I distributed my 1/3 into each of my logs that were left inside. So you get 2/3 plus 1/3 log AB minus 5/3 log AC. This one has every rule that we talked about today, and it has that special rule from last time, the log base A of A, in there. It's about as complicated as they get in terms of expanding. Are there any questions? So both of those were expand problems. So what do you think the next two are going to be? Condense problems. You are correct. They're condensed. So we're going to go from the long format into the nice, tight, small format where we have one logarithm with everything all bundled up together. So when you're going this direction with things, if there's a number out front, you can bring that inside of your logarithm using your power rule. And that's usually the easiest place to start. This 5 out front is going to come inside and be the power on my x. So that I have log base b of x to the 5th. There's no number in front of my next log, but there is in front of my last. Log base b of z to the 1/4. What would you do next? Okay, so we're going to combine these two using our division or quotient rule. And we saw this plus log base b, and then I'm going to go ahead and make this into a 4th root of z. If you have a rational exponent that's never going to be completely simplified, it's better for you to put it in a radical format. Okay, now what do I do?
Combine the two that are being added.
With what? Yeah. This is our product rule, so we're going to multiply, giving me log base b of x to the 5th, the 4th root of z, all over y. I have condensed all of that mess into one quote-unquote nice logarithm. There's nothing left for me to condense or simplify or get rid of or anything. So that would be the end for us. Any questions on that one?
Yes.
Yes.
So, I understand why we put the two that are being subtracted into division. How do we know where the rest of that goes? Because whenever I was doing it
when you're multiplying, forget about the logs entirely and just think about if I was multiplying x to the 5th over y times this. This is not written as a fraction, this 4th root of z. So you would stick it over 1. And when you do that, notice it's going to stay on top. Does that make more sense? So maybe sticking it over 1 would be helpful. Any other questions on that one? Okay. Let's do another one. ln of 3 plus 1, 3x plus 1, excuse me, minus ln of 3ax squared minus 5x minus 2. So I only have 2 logs at play here, and they're both natural logs, so I can combine them. Since it's subtraction, I'm going to use which of our rules? Product, quotient, or power? Quotient. So I can combine these bad boys into one fraction. So that I have ln, and the first term is my top. 3x plus 1. My second term, this quadratic, is my bottom. 3x squared minus 5x minus 2. And don't get all excited that you're already done, because you're not. Because if you're dealing with polynomials inside of your logarithms, especially if one of them is a binomial, like your top, and one of them is a quadratic, like the bottom, odds are stuff's going to cancel and simplify out. So in this case, I would strongly recommend we have 3x plus 1 on top. Let's see if we can't factor that bottom so that we have a 3x plus 1 on bottom. If I have a 3x plus 1, it's going to leave me with an x here. I need to get a 2 here, and it needs to be negative, so it's going to be x minus 2 there. What that does, though, is that gives me a 3x plus 1 on top and bottom, so that this actually fully simplifies to ln of 1 over x minus 2. So you definitely want to look for little things like that as well as we're working through these. If you've got a quadratic and a binomial in a fraction form like this, I always recommend whatever your binomial is, try factoring your quadratic into that binomial and seeing if stuff won't cancel. Typically it does. Questions? We've got one more little fun little rule, and then we'll be done. Okay. What this rule says is that if you have a raised to the power of log base a of x, all of that is going to simplify out to x. You're like, well, that's a mess of a rule. Kind of is. The reason why it works, base becomes the exponent. Is that right? Do I have that written right? Let me check. Yeah. Yes, I do. Base becomes the base, answer becomes the exponent. Oh, because we're going the other direction. So the base became the base. Our answer became our exponent. That's the way it goes. Did you follow me what I just did? kind of proving why this works. So remember, when we go from logarithms to exponentials, that's the base becomes the base, the answer becomes the exponent thing. So if I'm going from an exponential into my logarithmic form, then the base of my exponential becomes the base of my logarithm. The answer of my logarithm became my exponent. So the answer was my logarithm. And my answer here for my exponential is what I was taking the log of. I'm just trying to show you how by the definition of logarithm, it actually does hold true that a raised to the log base a of x actually equals x. Okay. Basically, this is one of those rules, kind of like the log base a of a equals 1. That's just a good thing to memorize because it's going to help you in terms of simplifying. I will tell you, though, I've taught college algebra for over 10 years. You don't use it all that much. You use these other ones a lot. You use the quotient rule, the product rule, the power rule, and this log base a of a. We use that quite a bit. This one's more of an anomaly that comes up every once in a while. That's why we're covering it here at the very end of the section. Trying to get both of it up there. There we go. And that's a really wonky looking 5. I messed up when I was writing it. Basically, what you're going to look for with problems like this is you're going to say, okay, is the base of my exponential also the base of the logarithm inside of the exponent? Because if that's the case, then you can ignore everything besides what you're taking the log of inside of your exponent. So I'll say it again. If the base of your exponent is the same as the base of the log that lies inside of your exponent, then we can ignore all of this stuff and just focus on what we're taking the log of. So all this stuff falls away to where 4 raised to the log base 4 of k is just simply k. So what would B be? B is 5. Because remember, ln means you have e to the log base e. So all of this would cancel, giving you 5. And what about C? 7t. If there's not a base written next to your log, that's where we consider it to be the common log, which means it has a base of 10. We talked about that last time as well. We don't write that in, just like we don't write the little 2 usually on the square root sign just because it makes it overly cluttered. And so these do share the same base, so all of that would go away, giving you 7t.